Welcome back to Fun Facts Online. Today, we are tuning into a frequency that has been silent for far too long. If you look up at the night sky, it seems quiet. But if you know how to listen, the universe is actually screaming. For decades, astronomers have scanned the cosmos in the quiet hum of the radio spectrum. They have picked up the metronomic pulses of rotating neutron stars. They have heard the chaotic roar of black holes devouring gas. They have even detected the faint, fossilized whisper of the Big Bang itself. Yet, in the search for the most profound quarry, planets like our own, orbiting distant stars, the radio sky has remained frustratingly silent. That silence broke 3 days ago. On January 27, 2026, a team led by researchers at the Paris Observatory and the University of Hertfordshire announced a paradigm-shifting discovery in nature astronomy. Using a novel processing technique known as Multiplexed Interferometric Radio Spectroscopy, or RIMS, they pulled not just one, but dozens of coherent radio signals from the archival noise of the LOFAR telescope. These were not the random bursts of stellar flares, nor the steady beacons of pulsars. They were the distinctive, polarized songs of worlds interacting with their stars. These are the first definitive space weather reports from alien systems. This breakthrough marks the dawn of a new era in astrophysics, the age of stellar radio spectroscopy. It is a field that promises to decode the invisible magnetic umbilical cords connecting stars and planets, revealing secrets about exoplanetary atmospheres, interiors, and ultimately, their capacity to harbor life. To understand the magnitude of this moment, we have to journey into the invisible architecture of magnetic fields, the violent dance of plasmas, and the technological marvels that have finally allowed us to hear the music of the spheres. To appreciate the sudden flood of data, we first have to understand the drought that preceded it. Since the dawn of the exoplanet revolution in 1995, when Michel Mayor and Didier Queloz discovered 51 Pegasi b, our knowledge of alien worlds has been dominated by two methods. First, the transit method, which looks for shadows as a planet crosses a star. Second, radial velocity, which looks for the wobbles a planet causes in its host star. These techniques are brilliant, but limited. They tell us a planet's radius, its mass, and its orbital period. With the James Webb Space Telescope, we began sniffing their atmospheres, looking for chemical fingerprints like methane or carbon dioxide. But a planet is more than just a ball of gas or rock, it is a dynamic engine. Deep inside Earth, churning molten iron generates a magnetic field that stretches thousands of kilometers into space. This magnetosphere is our shield. It is a force field that deflects the stripping power of the solar wind. Without it, Earth might have shared the fate of Mars, a cold, desiccated husk whose atmosphere was scoured away billions of years ago. If we want to know if an exoplanet is truly habitable, we need to know if it has a magnetic field. But magnetic fields are invisible to optical telescopes. They don't cast shadows. They don't wobble the star. However, under the right conditions they do sing. In 1955, serendipity struck just outside Washington, D.C., where astronomers accidentally detected bursts of radiostatic coming from a specific patch of sky. It wasn't a star, or a galaxy. It was Jupiter. We now know that Jupiter is a radio lighthouse. Its magnetic field is 20,000 times stronger than Earth's. As its moon Io orbits, it spews volcanic plasma into Jupiter's magnetic environment. This plasma creates a conductive circuit, essentially a physical wire, made of charged particles connecting the moon to the planet. As Io moves, it plucks the magnetic field lines of Jupiter like a guitar string. This generates powerful currents that accelerate electrons toward Jupiter's poles, causing them to spiral and emit intense, coherent radio waves. This phenomenon is known as the Electron Cyclotron Maser Emission, or ECME. For 50 years, astronomers reasoned that if Jupiter emits these signals, massive hot Jupiters, those gas giants orbiting furiously close to their stars, should be radio flashlights, blasting out signals thousands of times stronger. Yet every time we looked, we saw nothing. The problem was twofold. First, the universe is noisy. The galaxy is awash in synchrotron radiation, a background hiss that can drown out faint planetary signals. Second, and more importantly, was the ionospheric cutoff. Earth's own atmosphere is a plasma shield. It blocks low-frequency radio waves, specifically those below 10 MHz, from reaching the ground. If a planet's magnetic field is weak, its radio emission falls into this blocked frequency range. We were like divers trying to hear a whisper from the surface while underwater. The breakthrough of 2026 didn't come from a new telescope launching above the atmosphere, though those are coming, but from a realization that we were looking for the wrong kind of signal in the data we already had. This brings us to the science of stellar radio spectroscopy. It isn't about taking pictures. It is about analyzing the dynamic spectrum of radio waves, tracking how their intensity changes over time and frequency. To decode these signals, we have to understand the three primary mechanisms of star-planet interaction. The first mechanism is the subalphenic interaction, also called the unipolar inductor. This is the Io scenario scaled up to stellar proportions. It occurs when a planet orbits so close to its star that it sits inside the star's Alfvén surface. The Alfvén surface is a theoretical boundary in the stellar wind. Inside this boundary, the magnetic pressure of the star dominates the kinetic pressure of the wind. More importantly, information can travel backwards to the star. Imagine a hot Jupiter plowing through the magnetized corona of its host star. Because the stellar wind is moving slower than the Alfvén speed, which is the speed at which magnetic waves travel, the disturbance created by the planet can propagate back down the magnetic field lines to the star itself. The planet acts as an obstacle, creating two wings of Alfvén waves that stretch back to the stellar surface. When these waves hit the star's atmosphere, they drive massive electrical currents. These currents accelerate electrons, generating auroras on the star. We aren't seeing the planet's radio emission. We are seeing the star screaming because the planet is poking it. This mechanism produces a signal that is modulated by the planet's orbital period. It turns on and off like clockwork as the magnetic connection sweeps across our line of sight. The second mechanism is the bow-shock interaction. For planets orbiting further out, like the Earth, the solar wind is supersonic. The planet creates a bow shock, like a boat moving through water. The planet's magnetosphere slams into the stellar wind, compressing it. Electrons are accelerated at the shock front, spiraling in the magnetic field and emitting synchrotron radiation. This signal is weaker and harder to distinguish from general background noise, but it is the holy grail for detecting Earth-like magnetospheres. The third mechanism involves reconnection events. Magnetic fields hate to be crossed. When the magnetic field of a star and a planet collide with opposite polarities, they can reconnect, snapping into a new configuration. This snap releases explosive energy, accelerating particles to relativistic speeds and triggering massive radio bursts. These look like stellar flares but occur with a periodicity linked to the planet's orbit. The January 2026 breakthrough hinges on RIMS, or Multiplexed Interferometric Radio Spectroscopy. The challenge with previous observations, particularly with arrays like LOFAR or the Murchison Wide Field Array, was the sheer volume of data. To find a planet, you traditionally need to stare at a star for hours, filtering out millions of terrestrial interference signals like FM radio, digital TV, and military radar. Traditionally, astronomers would pick one target, stare at it, and process that tiny slice of data. It was like looking for a needle in a haystack, by examining one straw at a time. RIMS changes the game by treating the entire sky as a single, interconnected dataset. It uses interferometric multiplexing. Instead of forming a single beam to look at one star, the RIMS algorithm utilizes the full correlator output of the array to synthesize thousands of virtual beams simultaneously. It combines this with temporal filtering. It looks for signals that are not just bright, but coherent. Natural astrophysical noise, like a supernova remnant, is incoherent. It is just broad static. The ECME from a star-planet interaction is coherent. It acts like a laser, but in radio. The waves are in lockstep. The team reprocessed 1.4 years of archival data from the LOFAR survey. They weren't looking for new data. They were mining the trash bin of previous surveys. The result was over 200,000 previously unidentified radio bursts. Among them, a distinctive subset of signals from red dwarf stars perfectly matched the theoretical predictions for star-planet interactions. The initial findings from the RIMS analysis have begun to populate a zoo of magnetic behaviors. Let's look at three specific examples found in the data. First, the hot Jupiter beacon, Tau Boötes b. One of the first systems to move from candidate to confirmed status in this new era is Tau Boötes. The planet is a massive hot Jupiter, orbiting its star every 3.3 days. The radio emission detected here is not constant. It arrives in slow, periodic bursts. This confirms the pulsar-like nature of the interaction. As the planet passes through specific magnetic longitudes of the star, the Alfvén wing connects, the circuit closes, and the radio beam sweeps across Earth. This implies that Tau Boötes b has a magnetic core capable of generating a field similar to Jupiter's. Second, we have the red dwarf dynamo, GJ1151. This system was the teaser trailer for this entire field. In 2020, LOFAR detected a low-frequency hum from this quiet red dwarf. The star itself is old and inactive, so it should be emitting radio waves. The new RIMS analysis confirms that this emission is driven by an unseen Earth-sized planet. The planet is likely an electrically conductive rock, or perhaps has a magma ocean that acts as a generator as it orbits, inducing currents in the star's corona. It is a unipolar inductor on a galactic scale. The twist here is that because the star is a red dwarf, its habitable zone is very close in. This means habitable planets around M dwarfs are almost certainly in the sub-Alfvénic regime. They are physically plugged into their stars. This has terrifying implications for habitability, because the direct magnetic connection could funnel stellar protons directly onto the planet's atmosphere, potentially stripping it faster than if it had no magnetic field at all. Third, we have the Proxima Centauri mystery. Our nearest neighbor is a flare star. It spits out X-rays and UV radiation constantly. Radio bursts have been detected here before, often attributed to flares. However, the new spectroscopy reveals a component of the radio signal that is synchronized with the orbit of Proxima b. The data suggests Proxima b is being buffeted by super-Alphinic pressures during flares, compressing its magnetosphere to the surface. If Proxima b has an atmosphere, it is being crushed and expanded rhythmically. The radio data allows us to map the Joule heating, the energy being dumped into the upper atmosphere of the planet. Why does this matter to the average person? Because the search for life is, at its core, a search for shields. We often talk about the Goldilocks Zone in terms of temperature. Not too hot, not too cold, but there is a magnetic Goldilocks Zone as well. If a planet's magnetic field is too weak, like Mars, the stellar wind strips the atmosphere, and the planet dies. Paradoxically, if the field is too strong, it might trap too much radiation, creating radiation belts so intense they sterilize the surface. And as seen with GJ 1151, if a planet is too close, its magnetic field couples with the stars, turning the shield into a funnel. Stellar Radio Spectroscopy gives us the tool to measure this. By measuring the cutoff frequency of the radio emission, we can calculate the magnetic field strength of the planet. The frequency of the Electron Cyclotron Maser Emission is directly proportional to the magnetic field strength. Specifically, the frequency in megahertz is roughly 2.8 times the magnetic field in Gauss. If we detect a signal cutting off at 30 megahertz, we know the planet has a magnetic field strength of roughly 10 Gauss, significantly stronger than Earth's 0.5 Gauss. For the first time, we can look at an Earth-sized exoplanet and say, it has a shield, it has a chance. The RIMS breakthrough is just the software opening the door. The hardware is about to kick it down. Construction is well underway in Western Australia and South Africa for the Square Kilometre Array, or SKA. When SKA-Low comes online later this decade, it will be roughly 50 times more sensitive than LOFAR. SKA will not just detect these interactions, it will image them. It will allow us to see the tomography of the stellar wind, mapping the density of the plasma between the star and the planet. We will be able to watch a coronal mass ejection leave a star and impact a planet in real time. Then there is the lunar frontier. The ultimate limit for ground-based astronomy is the ionosphere. We simply cannot hear frequencies below 10 MHz, which is where the magnetic signals of Earth-like planets with weak fields live. The solution is to go to the Moon. The Lunar Surface Electromagnetics Experiment Night, or LUCY Night, is a Pathfinder mission scheduled for the far side of the Moon. Shielded from Earth's radio noise and lacking an ionosphere, it will open the Dark Ages window of the radio spectrum. A full lunar array could detect the auroral radio emissions of an Earth twin around a Sun-like star. This is the only way to confirm if a true Earth 2.0 has a magnetosphere. We have spent 30 years collecting the stamp collection of exoplanets. We have sorted them by size, by mass, and by orbital period. We have marveled at hot Jupiters and wondered at super-Earths. But until now, they have been static objects in our minds, silent spheres hanging in the dark. Stellar radio spectroscopy has turned the volume up. It has revealed that these systems are not static. They are electric, dynamic, and violent. They are webs of energy, where stars and planets are locked in a constant electromagnetic exchange. The detection of these radio signals is more than a technical triumph. It is a shift in our cosmic perspective. It reminds us that habitability is not just about having water, it's about having a defense. As we tune into these alien broadcasts, decoding the hiss and crackle of magnetic reconnections, we are essentially listening for the heartbeat of living worlds. The silence is over. The universe is speaking. And, for the first time, we know the language. Thanks for listening to G Fun Facts Online, and we'll catch you in the next episode.